Hi everyone, welcome back to Dr. Tutor. Today we'll be continuing Unit 3 of QCE Chemistry, Topic 1, which is chemical equilibrium, and today's topic specifically is factors that affect equilibrium and LCP, which is Le Chatelier's principle, which is something you will unfortunately have to become intimately familiar with in the next year or two. So before we start today's topic, I just want to ask you guys to like and subscribe so that you can get a good ATAR, thank you. Moving on, so Le Chatelier's principle. Basically, what it says is, if an equilibrium system is subjected to a change, it will adjust itself to partially oppose the effect of that change. So the question is how? So what that basically means is that if something happens, system no likey. And what I mean by that is that chemical equilibrium systems are really afraid of change, and they really don't like things happening to them because they are scared. And so what they do is, if you try to do something to them, they will try to fix it. Not that they have feelings or anything, don't say that in your exam, but for the sake of learning and conceptualizing, we can pretend like the system has feelings. So yeah, basically it no likey the change, and so what it does is it shifts its equilibrium position, if you remember from last video. It'll shift to either the right or the left, depending on which side is better to try to oppose the effect of the change. So let's look at some examples. If you increase the temperature, that's our first one. If you increase temperature, then the system wants to decrease temperature, and it does that by favoring the reaction which is endothermic. So favoring endothermic. So whichever reaction is the endothermic one, and remember from last video, we learned that endothermic reactions are the ones which take away heat, right? They use up more heat. And so, although this doesn't usually return the temperature all the way back to what it was before, it helps to oppose the change. And that's why we say partially oppose the change. Because, it can't just, set itself on fire or, turn on the aircon. So, it can just do its best to try to partially oppose the change. To talk physically, to talk chemically, the real reason why this actually happens is because now that there's more energy available in the system, right, we've added heat to it, so there's more energy available. What that means is that there's more energy for the endothermic reaction to actually use. It's easier for it to reach its activation energy, and so therefore it happens more frequently, as opposed to the exothermic reaction, which doesn't really need that extra energy, so it's kind of unbothered. But the endothermic reaction is like, oh my god, so much energy, let me use this all up. And so it happens more frequently, which means that it's being favored. And that's related to enthalpy, as we talked about in our last video. So this idea of being favored isn't actually the system waking up and choosing oh, I want to be really hot today. It's genuinely what just occurs as a physical consequence of whatever action you're doing to it. So I'll get back to this in 1 second. So then let's talk about our next example, which is going to be concentration. So if we increase the concentration of, let's say, the reactants, right, then the system, again, no likey, it wants to decrease the reactant concentration, right? Sorry, I should probably say concentration here. And it does that. I'm going to give you 1 second to have a guess of how it decides to do that and which reaction it favors. Have you figured it out? Hopefully, yes. If not, I will tell you. So, the reactant concentration gets decreased by literally just using up the reactants. So what it will do is it'll favor the forward reaction, which uses up the reactants. And then that will mean that, yeah, the concentration of reactants will decrease. That makes sense. So it favors the forward reaction. And then therefore, it's therefore reducing the concentration of reactant back down. Okay, again, probably won't be able to reduce it back to what it was before, but it will try its best. So again, there's a real physical, chemical reason why this occurs, and it's because of quote-unquote collision theory, which if you haven't heard of it, it's basically just the idea that chemical reactions occur when molecules collide at the perfect speed and the perfect orientation. So basically, for any reaction to occur between any two molecules, they kind of need to do a little kiss. And if they kiss too fast, then it doesn't work. And if they kiss too slow, then it also doesn't work. And if they kiss sideways, it also doesn't work. So it needs to be very perfect. And that's called collision theory. What happens is, when we increase the concentration of reactant, right, we literally just have more reactant molecules. And what that means is that these molecules are more likely to collide or kiss in the perfect way. And so that means that the reaction is more likely to happen. Again, this is an example of how the system doesn't just wake up and it's oh, I want to have less reactants. It's literally a physical consequence. So more reactants means more likelihood of them colliding correctly, which means more forward reaction happening, which means like the forward reaction is being favored. Okay, the same thing would happen if you like decrease the amount of products, for example. So if you somehow decrease the concentration of products in the system, then it wants to add more products back to the system, so it favors the forward reaction. And again, the real reason why this occurs is because now you have way more reactants than products, and so the reactants are more likely to collide, whereas the less amount of products is less likely to collide in the proper way. And so you would see that there's less of the reverse reaction happening because you have not that many products, so there's less chance, but you have heaps of reactants, so there's more chance, so there's more of this reaction happening. So yeah, basically, that's concentration. Okay, so moving on to pressure. You might be familiar with what pressure is, but I'll give you the technical definition. Pressure is the amount of force you have per area. If you have a balloon, and if you have a bunch of gas in that balloon, right, then you have like a certain amount of pressure. But if I keep overloading that balloon with like even more gas and even more gas until the balloon is really overfilled, then the balloon pops. And the reason why is because there's too much pressure being exerted on the balloon. So the more particles or the more molecules you have within a certain defined space, the more pressure you have in that space. And that pressure is like the force acting on the walls of that space because the molecules keep crashing into the walls. And so the more molecules you have, the more crashing is going to happen, and so the more pressure you have. If you increase the pressure, and remember, it has to be a closed system for an equilibrium reaction, and therefore the system will always have some kind of pressure, right? Because in any closed container that has like molecules in it, which it would have molecules in it, then it will have some kind of baseline pressure, right? So if you increase that pressure, and that can be either by decreasing the volume of the container. So if you make the container smaller, then there's less space for those particles to exist in, so they're more likely to crash into the walls of the container. Or if you just increase the number of particles in the container but keep it the same size, then now there's more particles, so there's more crashing, so there's more pressure. So yeah, basically if you increase the pressure or like decrease the volume, which is the same thing, then what will happen is that the system wants to decrease the pressure back down. And unfortunately, it cannot just like magically increase the volume, L. So what it has to do is it has to somehow favor some reaction that will have less pressure, right? The first thing to think about is that pressure changes are only really relevant in reactions that have all gases. This is like kind of gas only, because when you have liquids or solids, the change that you can get in pressure is pretty minimal, especially considering like even if you have a liquid in a container, it's not like that liquid is like harassing every edge of the container. It's just like sitting there, right? Same with a solid, it'll just like exist in the container. But when you have a gas, it's actually like literally bouncing off the walls, right? And so that will cause like more realistic pressure changes. However, because we're talking about gas, it's pretty difficult to change the amount of gas particles in a closed system, especially like if you're trying to decrease the gas particles. Like what are you going to do? Scoop it out. And so what usually we talk about is like an increase or decrease in volume. That's why it's really important for you to remember a decrease in volume means an increase in pressure, and an increase in volume, so like if you make the container bigger, that's a decrease in pressure because it's like harder for that many molecules to bounce off the walls. Like they spend less time crashing into the walls because the walls are further away. Okay, so yes, keep in mind, pressure inversely proportional to volume. As volume decreases, pressure increases, and as volume increases, pressure decreases. So, say the pressure in the system has been increased by decreasing the volume, therefore the particles are more tightly packed together, and like remember it's a gas, so they're more tightly packed and they're like crashing off the walls more. So the system will therefore want to decrease the pressure by reducing the molecules of gas. And you're like, oh, how is it going to reduce the molecules of gas? Well, usually in gas reactions, there's always one side of the equation that has less actual molecules. So on this side, we have 2 molecules, or like 2 particles every time, right? But on this side, we only have 1 particle. And so what that means is that on this side, if we had it all like this, there's less chance of that 1 particle crashing into the walls as much as there is for these 2 particles to crash into the walls, right? So we could have one system where it's like, say this is our container. In this system, we have like a bunch of these like 2 particles, and we have so many of them, right? I'm gonna draw this many. And then in this one, we can have half the number of these fatter molecules like this. And then see, in this system, there's gonna be less pressure, and in this system, there's gonna be more pressure. Why? Because in this one, there's only 4 particles that could possibly be bouncing off the walls. But in this one, there's 8 particles that could be going around bouncing on the walls. So therefore, the system will favor this situation, right? It would prefer to have this, since it wants to try to decrease the pressure, and so it'll favor this forward reaction here. I should probably have drawn this with an equilibrium arrow. Okay, so it's going to be favoring this way, and we could represent that by drawing this arrow like a lot bigger, and then just drawing a little arrow going this way. Okay, so something to note here maybe is that when a reaction is being favored, that doesn't mean that it's like completely, totally just doing that reaction. It will still always just be doing a little bit of the reverse as well, but it just like doesn't really want to, so it likes doing that one better. Once again, this only actually occurs because of collision theory, so like the system doesn't actually want to do anything. It's just literally happening because if there's less space, right, like if I've decreased the volume of this container, then there's more chance of these particles crashing into each other, and then therefore there's more chance of them getting turned into this, whereas in this situation, because there's less particles, there's less chance of them crashing into each other, so like it's basically the same thing as what we talked about with concentration. Alright, finally, the only last thing you need to know with Le Chatelier's principle is number 4, which is adding a catalyst. And adding a catalyst, okay, firstly, what is a catalyst? A catalyst is something that decreases the activation energy of the forward or the reverse reaction, and therefore the reactions can just occur more quickly because they need less energy to get started, therefore, like, they'll just get started more often and, like, faster and better. It doesn't actually have an effect on Le Chatelier's principle. I don't really know why they included it here, but what it does do is it causes the system to reach equilibrium faster because all the reactions required for it to reach equilibrium can just happen like better and faster because the activation energy has been lowered. But yeah, equilibrium position remains the same. Nothing really gets favored. It's just like everything just happens faster. That's the main thing. Okay, these are the 4 factors you need to know as per the curriculum. Again, I don't really know why they included catalyst, but like whatever. QCE, slay. Just to quickly summarize, let's just make a quick summary. So if we have temperature, number 1, temp, you need to consider enthalpy change when you're explaining, okay? So remember, as I talked about, like, if there's more energy available, then the endothermic reaction will use up that energy. And so that would be considered like discussion of enthalpy change. So when you're answering questions related to LCP and you're being asked to explain how LCP works, or like you have like one of those questions where you have like lots of lines to write stuff down, you need to make sure that if it's related to temperature, you somewhere mention enthalpy change and you talk about the fact that there's more energy available for the endothermic reaction to occur, or there's like less energy available for something else to occur, or just talk about something related to energy and why it would favor the endothermic or the exothermic reaction. So just to quickly summarize like what the actual answer would be. So if you increase the temp, then it will favor the positive delta H, which is endothermic. If you decrease, then it will favor the negative delta H, which is the exothermic. The way that I like to remember this is as temp increases, okay, and keep an eye on this, as temperature increases, if Kc, and I know you maybe don't know what Kc is yet, but I will talk about it in the next video, but just remember this for like a rule. If Kc also increases, then that means it's like favoring the forward. That's all that means, okay, so favoring forward. Then that means that the forward is endothermic. And this is just like how I quickly remember it because these all have like the En or the In. And then conversely, if Kc decreases, which means it's favoring the reverse, then that must mean that the forward is exothermic. The reason why is because if we have a temperature increase, right, then it would want to make sure to favor the endothermic reaction. So we know that if it's favoring the forward one, then the forward one has to be endothermic. But if the temperature increases and it favors the reverse one, then the reverse one must be endothermic. So therefore the forward must be exothermic. Okay, hopefully that makes sense. If it doesn't, it'll make sense after I tell you what Kc is. So stay tuned for the next video. Okay, and then number 2 is concentration. So for this one, you need to talk about collision theory. So remember how I was saying you need to talk about enthalpy if you're being asked about temperature. For this one, you need to talk about collision theory. And then if you have an increase in reactant, oh my god, okay, just ignore my absolutely horrendous spelling. If you have an increase in reactant or a decrease in product, I'll just use arrows. That might be more suitable for my poor English skills. Then that means that it will favor forward because it wants to use up those reactants or it wants to add in more product. Or if you decrease the reactants or increase the products, then it will favor the reverse because it wants to either add in more reactants, or it wants to use up those products, or both, I guess. Okay, then number 3 is pressure. Again, when you're explaining pressure, you need to talk about collision theory. And if you are increasing the volume, so if you're increasing the volume, that means you're decreasing the pressure, and that means it will favor the reaction that has more moles. So it favors the one more moles, or more molecules, if that makes it easier for you to conceptualize. And if you decrease the volume, then it's just the opposite. You are increasing the pressure, and so it'll favor the one with less moles. And then finally, number 4 is catalyst. You need to consider activation energy, so just talk about activation energy, and then basically adding catalyst causes a decrease in EA, therefore everything just happens faster, so it reaches equilibrium faster. And that's basically it. Okay, so that's LCP. Now, if you recall from the last video, I showed you a graph, and I was like, I'm not explaining this graph because it would be spoilers for the next video. So, here's the next video, and now let me tell you about this graph. Okay, so, don't worry about all this text right now, let's just worry about the main graph. So we have concentration here, and we have time here, as I talked about last time. And so this concentration is our y-axis, time is our x-axis, and what we can see here is we have some various products or reactants or whatever concentrations of things, and we can see that here they are flat. So that means that our concentrations are stable, they're not changing, and that would mean that during this period the system is in equilibrium. Okay, now, say we introduce some kind of change. So if we see a sudden change like this is our change. If you see a sharp and sudden change, that means it's something that's been forced externally, right? So that could either be a change in concentration, or if all of them change, then it would be a change in volume. But just if it's just one, right? If one of them suddenly increases or suddenly decreases, that means it's a forced change in concentration. So say this one is increasing, that means we've added some of whatever this is to the system. If all of them change, right? So if all of them have a sharp increase or have a sharp decrease, then what that would mean is that we've changed the volume of the system. And how do we know that? So again, a sharp or sudden change always indicates a forced change, or the change that you as the scientist have caused on the system. Whereas these slow curve changes are usually a reactive change. So that's what's happening in response to the change you forced. So that's how you can tell what's going on. Imagine if we have all increases here. So if all of these increase sharply, right, then that would mean that the concentration of everything is increasing. And probably the most realistic way that's happening is by decreasing the volume of the container, because if we decrease the volume, then we automatically increase the concentration of everything that's in there, right? Because concentration is just the amount of stuff per area. And so if we are decreasing the area for that stuff to exist in, then we're increasing the concentration because there's less area and there's still the same amount of stuff. And so it's very unlikely that you for some reason have decided to increase the concentration of everything by adding more stuff in. It's more likely if you see something like this that it's because of a change in volume and therefore a change in pressure. Similarly, if everything decreases, then that would mean that you've increased the volume and therefore decreased the concentration of everything at the same time. Also, the other reason why it would be really sus if you increase the concentration of everything is because it would be really difficult for you to pour all of it in at the same time. So just think in a practical sense, it's probably more likely that you just squish the container. Okay, so in this example, we have a sudden change for just one of them, which means that it's probably just an increase in concentration, so you've just added in more of this, whatever this molecule is. And what that causes, effectively, is now the system wants to decrease this back down because of the Chatelier's principle, because it doesn't like change, no likey. And so, what it's going to do is it's going to have this reactive, slow curve reactive change that tries to decrease this particular thing down. Now, we can also notice that this one is also decreasing down, whereas this one is increasing up. And what that tells us is that, say this is a product, right? Let me write this in quickly. Say this is a product, and this is a reactant. That would show us, effectively, that when we increase the concentration of one of our products, the system wants to decrease it back down. It so happens that because this is also a product, this will also unfortunately get decreased as well. And that's because since we're going to be favoring the reverse reaction to be using up this particular product, right? Because we want to get rid of it, so we want to use it up. That means that we're going to accidentally use up all of the other products as well. And that's why we see that this one also decreases, right? But this one is increasing. So we know that that can't be a product because the whole point of doing this is that we're trying to use up the products. So this one actually has to be a reactant because as we use up the products, we're using them to make reactants. And so that means that this one is going to be a reactant. It's totally possible that this is actually a reactant, this is a reactant, and this is a product. But the thing that I'm trying to teach you is that if they're decreasing, the ones that are decreasing or increasing together are the same thing, and then the one that's doing the opposite is the opposite thing. That's pretty much what this text says. So this is oppose the change by going down. This one is increased though, so like that's fine, whatever, it doesn't really care. And we can see that eventually, after this red line, we see that we've established a new equilibrium. So again, all of these lines are flat now. That means that the concentrations are stable, they're not changing. And so we've established a new equilibrium. Some quick things to note as well is that it's not quite back to the original equilibrium, since remember, LCP only allows systems to partially oppose a change, not fully. If it went like all the way back down to the original equilibrium somehow, that would be crazy. It cannot do that, it doesn't know how. But what we will see is that it kind of like goes back to a little bit normal, right? Then the other thing to note is that the other time where you get slow changes like this is when you have changes in temperature. So when you see a slow curve change, it's not always a reactive change. It could also be that you're increasing the temperature, because usually you can't like force the temperature to increase in one big stick like this. You would kind of have to increase it over time. And so when you see that, that could also be a temperature change. And then yeah, finally, if it's a catalyst, then it'll just speed everything up. So like instead of, say if you've like also added a catalyst, like what if they tell you like, oh, this is where we added a catalyst? Then you would just see that instead of it like going down like this, it would just like go down like this. Like it would just be like really fast. And like same with this, instead of like going down like this, it would just go down like that. Or like instead of like this, it would just go like boom. So congratulations. Hopefully now you understand the Chatelier's principle. If you don't, feel free to comment down below and I will try my best to explain in the comments. And if you want a complete subject guide for chemistry, you can go to the link below, or you can get an active ATAR membership, which gives you literally educational content for every single subject that I have made so far, as well as thousands of practice questions with all detailed explanations and answers. You can also directly book online tutoring and assignment help sessions if you need, and basically please like and subscribe and send this video to your friends if you like them and you want them to score well in chemistry. Thank you, bye!